Hey guys, welcome to this talk on deep learning for medical image reconstruction, model priors and data. My name is R van Sloun. I'm an assistant professor at the Technical University of Eindhoven in the Netherlands. And today I'll hope to share with you a little bit of a journey of deep learning in medical image recon, how we can use it, what gaps we are filling with respect to classical methods, and say the opportunities that we have in this domain. So let's get started. So image recon is important for MRI, CT, ultrasound, all with their own challenges and opportunities for image recon. In MR, we typically want to go faster because MR is slow, and these machines are bulky, so we want to make them more compact, which you can do by using low field applications. So these are challenges in image recon, as we shall see later. In CT, you have similar challenges. You want to go low dose, you want to go sparse view, and retain the image quality. And in ultrasound, you want to have the high image quality at, I'd say, reduced data rates. So let's get into the basics of image recon, because that's going to be important and it's going to lay the foundation for, say, the solutions that we're going to present. And let's start with ultrasound. So let's take an ultrasound probe. An ultrasound probe is going to fire a transmit pulse into some tissue, as you can see here. And then the nature of ultrasound imaging dictates that, tissue is going to, at interfaces, impedance mismatches, is going to reflect this TX pulse. And what you will see is an RX signal that looks like this. So we fire away and we get an RX signal that's going to reflect at the interfaces, but there is also, of course, reflections in between. So you see that we're not just getting these reflections from the edges, which is, say, the coherent reflections that you get back from these strong interfaces between tissue. But you also get this kind of incoherent summing of sub-wavelength scatterers that are distributed in the tissue. And that's what we call speckle. We'll get to that in a little bit as well. And the image is finally formed by estimating reflected signal amplitude locally from a set of spatial locations, pixels, right, using an array of sensors. And that is called beamforming, right? So we use this array of sensors not only to boost the SNR of the individual channels, the individual signals, but also to focus our energy and probe literally spatially the acoustic energy that's reflected from spatial regions. And the better you can do that, the better your imaging is. So if you look at the imaging chain, it starts with a transmission. You start by transmitting an ultrasound signal into, say, tissue, and then you're going to receive this scatter reflection. So this is kind of a two-stage approach where you first fire a transmit, and this transmit can be focused, you see here, but there are also other kinds of transmissions, as we'll see in a little bit. And then you start to listen. So you switch between these two modes, transmit and then receive, and on the receive end you are receiving this channel data, which are hundreds to thousands of channels that are received at the same time, and that are going to lead to high data rates once we turn them to digital, right? So we have all these data sets that are going to be converted to digital using high rate ADCs, typically between 20 and 50 megahertz per element. So that's a lot of data. And then once we're in the digital domain, we will do digital beamforming, also called spatial filtering, right? And then from all of that channel data, you form basically one reconstructed RF scan line based on, say, that single transmit. So in this case, we were using a focused scan line. You see that we're transmitting a wave into tissue, which is focused. And then we have this channel data that is going to be used to reconstruct, say, a single RF scan line. And then we scan, so we go from, say, one line to the next, and we in that way form our image step by step. So one of those RF scan lines, which are like the spatially filtered set of channel data, right? We're using this array to do spatial selectivity. One of those scan lines is going to be then one line in the image, as you see here on the right. Now the question is, how much signal is reflected from a particular pixel? Because that is what you want to do in digital beamforming, right? So in digital beamforming, the goal is to do spatial filtering. So you want to know how much signal is reflected from a particular pixel. And the measurement is in principle compromised by things like side lobes, grating lobes, and we'll see in a bit where they come from. but also the main lobe width. So the resolution of the system, which is dictated by the physics of the system, is going to impact how precisely we can tell, in this particular point we are receiving this amount of energy, right? And the better this spatial selectivity, the better you're able to get rid of the side lobes, grading lobes, and make that main lobe width as narrow as possible while being very sensitive, the better your tissue contrast and resolution. Because in the limit, if you would be able to locally probe exactly the energy that is reflected from that individual point, that is like the best possible thing you could do in pulse echo imaging. So in ultrasound imaging, the image quality is a function of two things. It's a function of the physics, of course, the array geometry, the probe bandwidth. If you increase the aperture, the size of the array, then you increase resolution, as you see here, right? So if we move from left to right on this set of graphs, you see that for 4 sensors that are spaced at, say half wavelength spacing, half lambda, you see that we don't have grating lobes because we're sampling at Nyquist rate, but we do have these side lobes, and we do have a given main lobe width, which is dictating our resolution. And if we increase the aperture, so we make the array bigger, we see that our resolution improves, and our side lobes are moving, are decaying more quickly as a function of angle. So that's one thing. So the array geometry plays a role, and the probe bandwidth plays a role, because with higher transmit frequencies or higher bandwidths, we can have higher resolution in the actual direction, in say the transmit direction. But also algorithms play a crucial role, because powerful digital signal processing and beamforming on this RF channel data is what is going to drive, the spatial selectivity, and is going to improve the selectivity regardless of the physical system. So if you have better algorithms, you can do more with the same kind of system. Yeah? And both of these are AI opportunities. You can use AI to design better systems. We've done some work on that as well, designing, array designs, things like that, based on learning. But the focus of today's talk will be about algorithms. So powerful signal processing, beamforming, image reconstruction algorithms on RF channel data to do a better job at, isolating and probing what the signal amplitude is from a very specific spatial region, with better spatial selectivity, better contrast, and better resolution. Yeah? So some of those opportunities are given on this slide. Let's start with parallel ultra-fast acquisitions, which is a trend that has come up over the past period. Ultra-fast imaging, where the entire medium is insonified at the same time. And that, of course, offers poorer spatial selectivity to begin with, because everything's backscattering at the same time. And that relies more heavily on, receive spatial filtering and beamforming. So it offers much higher time resolution, but it compromises the spatial resolution and the contrast as compared to these focused transmits, which take a long time because you have to line scan, right? You have to insonify, lines one at a time, or maybe sometimes you could do multi-line acquisitions, things like that, but it's inherently slower, so poorer time resolution. But yeah, the spatial resolution and contrast is typically better. So how can you use AI to improve that? That would be a question. Another question you could ask yourself is, how can we offer better image quality under, minimal data rates? How can we improve tissue contrast, achieve accurate contrast? How can we get a high resolution image with a small or a sparse aperture, as you see here? How can we achieve high resolution imaging with a probe bandwidth that's more limited, or a more low frequency transmit pulse? How can we achieve high resolution, high quality imaging under compressed sensing? So when we are sampling signals or channel data signals under sub-Nyquist rate, which has all sorts of benefits in terms of data rates and probe compactness. So these are some of those opportunities. So now, stepping away from ultrasound, let's have a look at the imaging basics of MR. Let's understand what's to gain over here. So in MR, what happens is that you acquire your samples in K-space. So in the 2D Fourier transform of the original image. And that is because MR has using pulse sequences to literally sample these spatial frequencies. And typically you sample lines, being radial lines or Cartesian lines, but typically you sample these kind of lines. And the total time it then takes for an MR machine to create an image is the time it takes to acquire one such line, which is the TR time here, times the amount of repetitions, so the amount of lines that you would need to take. And that limits then the time resolution of MR, right? So if you take more lines, your image quality will be better because you fill the K-space spectrum better. You see that in the video in the top right. And if you use less lines, then you have a better temporal resolution. So if we want to push down the acquisition time of MR, typically what is done is undersampling in K-space. Now, once we have this K-space, when it's really filled, when it's properly filled, you can use the inverse Fourier transform to then make an image. Now, if we look at undersampling in K-space, then there are indeed, as I mentioned before, a couple of undersampling patterns that are very typical. So radial sampling, there's also spiral sampling, and Cartesian sampling. And here, really less acquisitions means faster scanning. So if we want to do fast MR, that means that we want to use less acquisitions, right? Because the time that it takes to sample one of these lines is limited by the physics. So if we want to push this time down, we need to take less acquisitions. So in general, what happens in these kind of algorithms is that we take the full K-space and we perform some sampling on that. And then we have a reconstruction algorithm that tries to, given those, say, undersampled K-space samples, get the image that you would get with the full K-space. In order to do that, you need to add information to this processing chain. In fact, you could formulate this, as a couple of problems. So first of all, the sampling, like how should you sample? Well, that's an opportunity for AI. How can we learn how to do our sampling better? How does our measurement model look like, right? It's P of y given x. What's the probability of measuring a K-space acquisition given my underlying high resolution MR image X? And then we have a reconstruction algorithm which tries to make use of this, and it tries to basically estimate what the probability is and maximize that of the image given the acquired data Y. And to do that, it usually makes use of priors P of x. And another question that you can ask is how do you design these priors? And we'll see later that that is also a place where AI can play a role. Okay, so in image reconstruction, the opportunities that you get for MR are typically either fast MR, like we just discussed, so compressed sensing, using fewer acquisitions to accelerate MR, but using, say, AI techniques to overcome these aliasing artifacts that you then get, right? And this received quite a lot of attention with the, say, the Fast MR challenge that was hosted by Facebook AI and NYU Health. They launched a big challenge. Many teams participated to accelerate basically the time it takes to do an MR using deep learning to perform image recon. But you can also think of using more low field MRs, so smaller magnets. And smaller magnets means smaller, more portable MR machines. So that would be beneficial, compact MR machines. The problem is that with lower field strengths, the SNR in K-space becomes lower as well, so your high frequencies become less clear because they're anyhow already weaker, as we saw from the K-space examples before, and that typically leads to lower resolution. So that's what you see here in the bottom. Also an opportunity for AI. Of course, for computed tomography, we also have these kind of opportunities. I will not go too much in detail today about AI for CT, simply because we have, as a group, not worked on computed tomography, so I'll leave that to others. But there are also similar opportunities. You can think of low-dose CT, which is safer, less ionizing radiation, but it's lower SNR. Can you overcome that with AI? Sparse CT, reducing scan time, improving time resolution again. Lower dose, so if you use sparser transmits, it's a lower dose, and you will also need to deal with undersampling artifacts. So again, image reconstruction will need to deal with that. So in general, across these domains, MRI, CT, ultrasound, but in fact, almost any kind of imaging modality will rely for a large part on proper image reconstruction. Yeah? And this is where AI can help us, and this is also the focus of today's talk. So now that we have laid the foundation of at least some of these imaging modalities, and we understand a little bit in which domain AI could help us, let us have a look at that. Now, what gaps can we fill by learning? So in other words, what are the challenges in classical image recon based on our models, right? So we can have flaws in either the acquisition model, where some assumptions are incorrect or imprecise. So, you know, in the map framework, you would then say that Py given X is wrong, so our likelihood model is wrong. You could say that your statistical image prior, so actually the priors that you use to augment basically Py given X such that you can do maximum posteriori estimation, those statistical image priors that help you find the right solution out of all of those solutions that possibly would fit that likelihood model, those are not sufficiently expressive or accurate. So very often we rely in model-based processing on, for instance, sparsity of images, which does not necessarily have to be the case, and finding domains transformations in which, you know, functions are sparse and images are sparse is not necessarily trivial. And thirdly, some of these processing methods for, say, classical image reconstruction based on models are very slow. So they rely on iterative algorithms that are have high complexity because of their iterative nature. And sometimes these processes involve matrix inversions that are, you know, as n grows larger, scales cubically in terms of computational complexity. So that's definitely something to avoid as well. So these are typically the gaps that we can try to overcome by learning, in this case, deep learning. So looking a little bit into those different subcategories, let's look at models and priors for ultrasound and where they are lacking. So if we look at P of y given x, the likelihood of the measurements y, given some object x, then across the imaging pipeline and the set of applications, y could be either the RF data, so that's the RF channel data, which is basically the response of the array. You see that here in the image as well. It's after sampling. Y can be beamformed RF data, so then it's after digital beamforming, or it could even be image data, so beamformed plus envelope detected data that you could use for, say, advanced signal processing or image processing applications. So let's look at one of the most common ones, which is the first, the channel data. So if you would formulate, so let's take a couple of assumptions now that we have a narrow band, single target, so a single source that is transmitting echo waves after we insonified it with a pulse. Then the array response that you would get off that single target would be y of t equals a of theta times x of t plus n, where y is the measurement, so that it's a vector. It's a vector that measures samples over time. Then after that we have the array response factor, which is a function of theta, the angle, and we have noise, which is typically assumed to follow a Gaussian distribution being spatially white. So all elements have independent noise and it all follows this Gaussian distribution. Now the MSE optimal matched filter for this particular array response is given here, where W equals A, and that's a matched filter. And the equivalent for the, say, wideband case that we actually have in ultrasound imaging is delay and sum beamforming. Yeah, so given all of the assumptions that we have here, so spatially white noise, this particular array response factor, which assumes this constant speed of sound, no aberration, etc. Given all of that, only one source transmitting. Given all of that, you know, this is, say, our optimal matched filter. But in practice, you know, the speed of sound is not constant. There is aberration, right? And this noise factor doesn't just consist of spatially white noise. There's sensor noise, which can even be coupled. There's off-axis scattering and interference. There's multiplicative noise. There's reverberation. So in practice, the statistics of the noise are highly complex. And all of this makes that, you know, this simple MSE optimal match filter being delay and sum is not optimal in the practical scenario. So some of the model-based alternatives to delay and sum are minimum variance distortionless response. So that's one common one. MVDR tries to minimize the total power, right? So the total response, but retaining unity gain in the direction of interest, right? So in this case, that would mean that you would apply a filter that has unity gain, so that is distortionless in that sense, but at the same time minimizes the total power in the output. So in that sense, it tries to suppress everything as much as possible while maintaining that unity gain. So IMAP is a maximum a posteriori estimator with a very simple signal prior, being x of t following a Gaussian distribution. And then iteratively, IMAP estimates sigma x or sigma n per pixel, and that way converges to a solution. So that's a maximum a posteriori solution with a very simple prior model. You could say a naive prior model, because if you look at these ultrasound images, definitely these sources do not follow a Gaussian distribution. Admire is a more complex model-based alternative to delay and sum. It's an aperture domain model of signal and noise, interference and clutter, which is then separated using optimization methods. So these are some of the model-based alternatives to delay and sum, but in practice, delay and sum is used in all clinical systems. Why? Because it's so simple and it is very fast. But it does violate a lot of these assumptions. So the general problem, even the general problem, say, with all of these other model-based optimization algorithms that we see over here, such as the MVDR, which tries to minimize the total power, IMAP, and Meyer. General problem is either that the model is too simple, so Py of x, the acquisition model, is too simple, it's incomplete, but it can also be that it's too hard to solve, and with that I mean recovering x from y is too hard due to a suboptimal prior. Right? So if we want to maximize the probability of x given y, if we assume a uniform prior, then that's equal to maximizing Py given x under x. But we know that that is definitely suboptimal, and you know this IMAP algorithm has a naive estimate for that prior. But in general, having more intricate, more complex, more powerful, more expressive priors will allow you to tackle these problems in a better way. So these are some of the, say, opportunities and challenges in the ultrasound domain. Another thing is that some of these solvers, in particular MVDR, are very slow. So MVDR relies on inversion of an estimated inverse. So it's inversion of estimated autocorrelation matrix. And that is slow, especially if the amount of array elements goes up. So for a large amount of array elements, this scales cubically, as I said before, in the number of array elements. And imagine doing this for a matrix transducer, which has a two-dimensional set of array elements that can easily be something like over 1,000 elements. Then that is extremely slow, and you have to do this for every pixel in pixel-based beamforming. Yes, because you're locally finding the optimal filter for every pixel. So what does that look like for MR? In MR, the likelihood of measurements y given object x are dictated by the measurements that we're doing in the k-space. So in MR, we're sampling lines or coefficients in k-space, which is the 2D Fourier transform of the underlying image. So you can formulate the measurement as a linear problem where we have y equals af x plus n, where we try to recover x from y under this subsampling matrix A and into the Fourier transform f. And note that for a low field, n is very strong, so n is a noise source that is dominating the higher frequencies. While for fast MR, A is a matrix that is sampling k-space below the Nyquist rate, so that's a compressed sensing setting. And the classical way to reconstruct x out of y is to simply do an inverse Fourier transform, where you see here that I also wrote down as z being the zero-filled k-space y. So if you would subsample, then you would first zero-fill and then perform an inverse Fourier transform. You can also do this in a maximum a posteriori fashion, where you solve the following inverse problem. You try to maximize the probability of y given x times p of x, which is the probability, maximizing the probability of x given y, and you can formulate that in the following as a following minimization problem under some conditions, namely that the likelihood model p of y given x is a Gaussian measurement model, right? So it's the measurement model we see on the top, where n follows a Gaussian distribution and is uncorrelated. In that particular setting, this maximization problem becomes the following minimization problem, where we have a least squares term, which is y minus afx, and we have a prior term on the right hand side. And this all boils down to choosing a proper prior in this sense, right? So you can solve this problem when it's very underdetermined and when there's a huge amount of noise, when you have a very powerful and expressive prior p of x. And so that's the general problem in MR, finding a prior p of x that is sufficiently expressive, and typical, say, model-based priors based on sparsity are not sufficiently expressive. So the question now is, with all of this and all of this knowledge and all the gaps that we know these model-based algorithms have, the question that you can ask yourself is, what if we could improve these models using deep learning, but without ending up just throwing away everything we know about the problem that we try to solve? So that is the question, and let's dive a little bit into that. So the question is, how do you bring deep learning and model-based algorithms together to get the best of both worlds, right? So to get complex statistical models that we can learn directly from data and unify them with domain knowledge, sensor physics, inductive biases, and theoretical guarantees that we would get from model-based algorithms. And so how do we bring these two together to get the best of both? Now, to do that, let's take one step back. Let's have a look at model-based optimization. And in model-based optimization, the general recipe is to construct an algorithm based on a priori knowledge of the measurement process and statistical priors. So first we define a model with image of interest x, which is y equals ax plus n. This is a simple model that you all know. And let's try to recover x from measurements y. For that, you can formulate a maximum a posteriori optimization problem, which is maximizing the joint. So it's maximizing p of y given x times p of x, which is the same as minimizing over x the negative log of that term. Now, for given p of y given x, so for given likelihood models and priors, we can write this out more specifically. Let's first have a look at the likelihood model that we have above. So if we assume that our likelihood model follows a normal distribution, right? So that n on top, this noise model, follows a Gaussian distribution, then the likelihood model looks like this, where if we plug that in, the above minimization problem, we get something that is basically a weighted least squares problem plus a negative log prior term. Now, if we assume that noise is uncorrelated, then we get the regular least squares term. So that's that first Euclidean distance squared term minus log of p of x, which is the prior. And for very specific, say, variance of p of x, so for instance, for p of x following a Laplace distribution, then this becomes an L1 norm. And for those kind of particular choices, and there are many more, Gaussian p of x, right, that would be a L2 norm. There are many iterative solvers for these kind of choices. Think of ISTA, ADMM, etc. And these iterative schemes, they look like the image we have over here, where we have a input y and the output after every iteration x of k. And this block f is doing the same over and over again. It's just that its input changes because it becomes the output of the previous iteration. Right? So that is an iterative model-based algorithm with input y and output x. So let's have a look at that. Let's now replace this prior negative log p of x by a general regularization, so a regularizer g theta, which is parameterized by theta. And then we derive an iterative proximal gradient solver based on that, right? So iterative proximal gradient solvers are particular iterative optimization algorithms that deal with these kinds of problems. So problems where we are having a data consistency term, this, you know, the least squares objective and a regularizer. And what it basically does is it's a two-stage optimization where at every iteration you first move in the direction of that least squares problem. So you first try to do a gradient update with respect to that term, and that's your first step. And then you move the solution to its closest point, x, that satisfies the regularizer. Yeah, so then you solve this second minimization problem, which for particular choices G lead to an analytical expression for a so-called prox operator, which is a proximity operator. And that is why this is called an iterative proximal gradient solver, because it takes a gradient step in the direction of that least squares problem, and then a proximity step which moves it in the direction or projects it onto the regularizer. And it's important to realize that this proximity function follows from the prior. So P of x dictates this prox. And this is now a two-step factorized optimization problem that we can write in the following way. So what we can do is we can factorize this iterative scheme that we have on the left and basically divide it into two blocks for every iteration. We have this data consistency step in green, this F1, and we have a prox, which is a prior step. And the prior is dictating the proximity function, and that proximity function is part of that iterative optimization algorithm, which is still doing every iteration the exact same calculations, but its input changes every time. That's the output of the previous one. Now let's look at an example, one that you're also all familiar with, which is the sparse coding problem. So sparse coding is trying to solve y equals ax plus n for x with knowing that x is sparse. So basically that x follows a Laplace distribution when this negative log of p is a L1 norm. So the map problem for x is then minimizing over x this least squares term ax minus y plus lambda times the L1 norm of x. And intuitively, that is solving this problem. And we're going to move in this solution space where you see the L1 ball indicated in dashed lines, and you also see the least squares problem. And what we do is we take iteratively steps first towards the minimum of the least squares problem. So this ax minus y. We take a gradient step with respect to that, so that's a data consistency step, and then we iterate, so we take that step and we take a next step where we move this intermediate solution in the direction of the prior. So then we solve that minimization problem we saw before, this minimum of x given the L2 distance squared of x minus x hat at that iteration plus lambda times, in this case, the L1 norm of x. And interestingly, for that particular choice, so for the particular choice where this regularizer is the L1 norm, or a scaled L1 norm, lambda times the L1 norm of x, then this is a soft thresholding function. So then the proximal mapping is a soft thresholding function where, say, the flat region in the middle is dictated by lambda. If lambda is larger, that flat region becomes larger, and if lambda is smaller, that flat region becomes smaller. So this is a particular instance of the proximal gradient algorithm we just discussed, and that you are probably familiar with. And then we zigzag, as you see here, to the solution by iterating between these two terms. So if we look at that solution and we put that again in a kind of iterative loop, then we see that we have indeed that gradient update step. You see that here with the two blocks. We have the proximity operator, this soft thresholding operator, and this gradient update at every iteration is performed by taking y, multiplying it with mu times A transpose, where mu is the step size, and taking the previous x and multiplying it with the matrix, which is the identity matrix minus mu A transpose A. And that follows directly from the math, taking the gradient with respect to that least squares term. Okay, so what does this mean for deep learning? Because this has nothing to do yet with deep learning. Well, let's have a look. So what you can now do is take this model-based optimization algorithm and unfold it as a fixed complexity graph and then learn the parameters. And this is a process that is called deep unfolding. And you can see it in the following way, where we have this iterative model-based algorithm with input y and output x. It's an iterative algorithm, and we unroll that and we unfold k such iterations where we now can learn the parameters of each of these blocks, and that is called deep algorithm unfolding. And this gives you naturally a deep neural network that is derived from that iterative optimization algorithm. And this all comes from the work initiated a while back by Gregor and Recon and their ICML paper, and that started actually with sparse recovery, so sparse coding. Let's have a look at what this means, particularly for sparse coding. So deep unfolding for sparse coding, at that time also called LISTA, learned ISTA, basically took the original ISTA algorithm and unfolded it as a feed-forward neural network. And you see that on the right. And now you take all of these blocks that correspond to the gradient updates, and you learn them. You learn the whole thing end to end, and this gives you a neural network with matrix multiplications or convolutions. So these W's can also be convolutions, which have a neural network with a model-based layer that consists of these matrix multiplications, the particular structure of the optimization algorithm, but also very importantly, the activation function, which comes naturally from the prior, being the soft thresholding function derived from prior that x is sparse, right? And yeah, so in that way we have a neural network with a model-based signal prior baked into it. What you can also do if you don't really know the prior, right, or the prior is too complex to describe, you could take your original optimization algorithm, so the one you see over here, decomposed in this data consistency step and the proximal step, and ask yourself what is a good general choice for the prox of z in structured signals, so signals that have some structure, if you don't know p of x. And in general, it turns out that replacing this prox by a high-performance denoiser is a very good choice. So what this looks like is that you take your factorized proximal gradient algorithm, which we see on the right, and instead of the prox, which we would usually take as, for instance, the L1 norm or something like that, you would replace that by a properly trained denoiser, which can be a neural network, and that is plugged in, and these kind of methods are called plug and play priors. So these are plug and play methods. Yeah. So crucially, this is still a standard optimization algorithm. It is still iterative, it's not unfolded, but the prox is replaced by a high-performance denoiser. Now, if you take this and you unfold that structure, then you can also imagine that you have an unfolded deep network with many of these proxies replaced by deep networks that you train then end-to-end. Yeah? So then we unfold again this proximal gradient algorithm as a deep neural network, but now the generic case where we replace this proximal operator for every iteration, and now we have a fixed complexity graph, so an iteration becomes a layer in that network, with a smaller neural network, which is that denoiser that we talked about, or any other kind of, say, parameterized proximal mapping that you can train, and we train it end-to-end. And now you can either choose to keep f fixed, so f being a function of the, say, a data consistency term, right? So it's a function of the measurement model, or you can also learn that to accelerate the optimization across these 10 folds. So you can also choose to learn these gradient update matrices W1 and W2 jointly, And then we have this big network which follows the structure of the optimization algorithm on the left, but we train all the parameters, including the parameterized prox function, which is here a small neural network. So now let's put these ideas to the test and see in several use cases, which we will focus on MRI and in particular ultrasound. Let's put these to the test and see how they perform and see some examples. Let's start with ultrasound imaging. So across the ultrasound imaging chain, there are various opportunities, and if you would like to learn more about that, about the opportunities of deep learning and AI in ultrasound in the signal processing chain, there's a recent review that we did for the proceedings of IEEE that you can have a look at if you like. Let's start by zooming into some of these examples, and in particular we start with digital beamforming, spatial filtering. So what we see here is an adaptive beamforming scheme, minimum variance distortionless response beamforming scheme. We talked about it before, and it includes a geometry-based time-to-space migration, so that is mapping, say, the channel data versus time to space, so pixels and channels, and then adds a model-based adaptive apodization to those channels for each pixel. The problem with MVDR is that it's slow, it can have unstable matrix inversions, but very importantly, it actually relies on very accurate estimates of the statistics which you get from snapshots. So it needs to know this a priori model knowledge. Now what we did in this work is replace the MVDR processor, which is slow and relies on these, say, estimates of these statistics, by an AI agent. So what you have here is a deep network plugged into this model-based computational graph, and the AI agent learns fast and stable, actionable statistics and function from data. So basically it learns to implicitly do the right thing by training. And we train this whole chain end-to-end through the sum, through the agent, back to the geometry-based time-space migration. And the advantage of this compared to minimum variance beamforming is that it's much faster, and it learns these actionable statistics by relying on, say, all the training data that it has seen, learns these actionable statistics from very few snapshots and from the partial, say, observations that it gets, and that is an advantage. So looking at some of the images here, what we have on the left is delay and sum, in the middle the deep learning method, able, on the right the target, which is the MVDR. Then delay and sum has a lot of noise in the background, lots of clutter, strong side and grating lobes, while the deep learning method even manages to outperform MVDR, although it is trained on MVDR. Note that it's not trained to replicate the apodizations that MVDR produces, but it's trained to produce the same image. And what we see in particular is that, say, the denoising property of the deep network that we chose, it is an encoder-decoder structure which allows you to predict these apodizations in, say, a very compact latent space, and hence all high entropy noise will not pass. This denoising property stabilizes the whole weight prediction process and makes it actually more stable than the MVDR. So we see here that the peaks are sharper, noise in the background is removed, and the grating and side lobes are suppressed more. And if we look at an in vivo example here, we see something similar. So we see comparing the standard delay and sum to able based on deep learning, that we see much better contrast. So these little black areas indicated by the arrows, they are unlike in delay and sum, they are not cluttered in the deep learning method. And we see the plaque, this is an intravascular ultrasound image, we see the plaque with higher fidelity, sharper peaks, and the calcifications, for instance, are more clearly visible. So this is less clutter, higher resolution at high processing rates, real time, and high robustness. So we can also look at one step further down. So now we've done the beamforming. This is for a different kind of imaging mode, in this case high resolution plane wave compounding. But the goal here is to take a couple of say, beamformed RF images that are obtained under different transmit angles, so different plane wave angles. So we're basically insonifying the medium under different angles, and by that way trying to exploit the redundancy in there to get to a better, and say the joint information in that acquisition to get to a better reconstruction. And we start here by formulating a model again. So again, we take an acquisition model. We say we have an unobserved high-resolution object that we try to image with these multiple plane waves. And the imaging process is described by these matrices A1, A2, and A3, which are basically the point spread function matrices for the individual plane wave transmits. And then based on that model, we can formulate the inverse problem and derive our model-based deep neural network. So going a little bit more in detail, the network looks like this, where we have this deep unfolded architecture with the acquisition model being in these f of theta 1 and f theta k blocks. And we have these proximal networks, these proximal operators that are deep networks that are mapping, say, the solution after every step closer to the, say, distribution of the unobserved high-resolution object. And we train this whole thing end-to-end towards that unobserved high-resolution object. So what you see here is that the input images have a low resolution as expected. These are 3 images that are obtained with these 3 different plane wave angles. And the target has a very high resolution, which is compounded from many more plane waves than just 3, in this case 75. It's also achieved with a higher center frequency, so the resolution is higher. And what we see is that the deep network actually manages, so this model-based deep network manages to get very close to that target. So that is very nice to see. Now, once we have high image quality, we can take a next step and try to separate various sources in the image. So, for instance, one of the typical sources that you would like to extract in ultrasound imaging is blood versus tissue. And you're always measuring a combination of the two that you would like to separate. And in sort of acquisition model, you could sort of write that the acquisition that you do, Y, is a mixture of those independent signals under some transformations, WT and WB, being tissue and blood. And then the goal is to separate these two from that mixture. And for that, we're again going to use model-based deep networks based on deep unfolding, based on end-to-end training to solve that inverse problem. So first, let's have a look at that inverse problem and see what particular aspects of that inverse problem we can make use of. So if we formulate the optimization problem, then basically we want to find this combination of L and S, where L is our tissue component and S is our blood component. We're writing them as L and S because we assume here, and that's our model, our prior, that L is low rank, so tissue is low rank. A stack, say, of images over time of tissue is going to be low rank, it's spatiotemporally smooth, whereas blood vessels, S, they are sparse in space while smooth over time. So if you see red blood cells moving, right, if you look at various frames after each other, then they will be smooth. There's a continuous depiction of the vasculature, but they're sparsely distributed compared to tissue. And the total sum of the two we call D, the total data. So the data is equal to L plus S, the low rank component, the tissue, and the sparse component, S. And the way we formulate the optimization problem is to say, okay, we have to find components L and S such that together they are close to D, the total measurement, while S is sparse and L is low rank. And we do that by penalizing the nuclear norm on L and the mixed L1, L2 norm on S, which promote respectively low rankness and sparsity in space, smoothness in time. So if we again write a proximal gradient solution for that, then you get two solutions, one per iteration step. You get one for L, one for S. and L is basically a proximal mapping on top of the gradient step again, and the gradient step is what you see between brackets, where the proximal operator is the proximal operator of the nuclear norm, which is singular value thresholding. So you do a singular value decomposition and you threshold the singular values. Whereas for the sparse component, we have again a gradient step, but now for S. And then on top of that, we have a proximal mapping, which is thresholding. And that thresholding is again a mixed L1, L2 thresholding. So if we put that in a diagram, then we get something like this, where we have an iterative shrinkage and thresholding algorithm, so a proximal gradient solution for robust PCA, because this is called robust PCA, this optimization problem. And you see the iterative loop for both tissue and blood, and of course they are coupled because they're jointly optimized. Now we can take this iterative algorithm and unfold it like we did in deep unfolding, and then we have basically one layer in a deep convolutional neural network, which we call deep convolutional robust PCA. And this is work that we did together with the group of Janina Eldar at the Weizmann Institute. So what you see here is a layer where the activations in the layer are based on singular value thresholding and the mixed L1, L2 norm thresholding. And the structure of the layer is such that it's derived from the optimization problem that we see above, and in particular its proximal gradient solution in the form of ISTA. So this is again an example of using this domain knowledge, this model-based knowledge, to formulate deep networks. So this is really one layer in our deep network. Another example is contrast ultrasound, and in particular super resolution contrast ultrasound, where we try to predict, say, sparse distribution of microbubbles from and the locations of the microbubbles from the diffraction limited images. And the way we do this again with model-based deep learning, I will not go too much into detail now for the sake of time, but the principle is the same again. We formulate a model, we derive the iterations of the optimization algorithm for that, and derive the algorithm, and in this case we use the list algorithm for that. But what you see on this slide is the standard image, and when I move to the next slide you will see what the lista, the learned iterative shrinkage and thresholding algorithm based on that model does. So that looks like this, and this is that lista algorithm, a deep network where, say, all layers are defined and the structure of the layers are defined by the model-based iterative optimization algorithm, the iterative shrinkage and thresholding algorithm. So again, this is now a deep network with model-based domain knowledge embedded in it. And here are two snapshots, some insets of the vasculature, and you can clearly see that the resolution has greatly improved, where we now see vessels quite clearly with even tortuosity, branching, and very fine details that you could not appreciate before. Now moving on to a different application beyond ultrasound imaging, showing that these ideas are more generic than just for ultrasound. Let's look at a couple of things for MR. And in MR, we're going to look at actually another aspect of the same puzzle, which is to not just learn how to do good image reconstruction, but also to learn how to do good sampling. So to do the acquisition better, such that the image reconstruction can subsequently benefit from that, and we get the best possible image as an output. So the way that looks is like this. So like if you would learn acquisition, you would say ideally that you have a system that takes measurements, and based on those measurements you do an image reconstruction on the fly, and based on that you have a planning AI that is making decisions for the new measurements to take, and then you take the next measurement and you iterate until you have filled the case space within the time that you are permitted. And you can do this in MR because the time to take a single line in MR, as you see here, is sufficiently long to allow you to actually do these kind of computations. And so the physics give you that time in that sense. Now here, just to emphasize again what the importance is of using model-based deep learning, in particular for these kind of applications. Because if you use a model-based deep network, then this very elegantly factorizes your knowledge in the sense that sampling and reconstruction update directions are decoupled during training. Now what does that mean? It means that if you change the sample pattern, so you take a different kind of line set, right, then the neural network doesn't have to adapt to that itself. It will automatically do, because say all aspects related to the acquisition are directly updating f, right? So this function f, which is fixed here in this case, has all the say the acquisition sampling changes baked into it, so it's directly updated, and hence the neural network is just a very strong de-aliasing neural network that is generic for say many different sets of lines. So in that way, by decoupling them during training and factorizing that knowledge, right, they can be more trivially jointly optimized. So let's look at some results here. So this is an example where we learned a single sampling density mask for the full acquisition, right? So here we do not do active acquisition, but just sampling, say, a learned set of masks. And we do that by using Gumbel top K sampling. So that's a mechanism for categorical sampling that you can train using the Gumbel softmax relaxation. Now, without going too much into the details of that, what you see in this image is that by learning the sampling scheme jointly with the reconstruction model, you can see that it really matters if you learn your sampling properly versus simply naively selecting, for instance, just the low frequencies in the full K-space. And you can clearly see that for the same reconstruction model, you get not only a better PSNR, but it's clear from the image that you really get a better performance. So this means that regardless of how well you can do reconstruction, it does matter how you actually acquire the data. And by learning that jointly, you basically have another opportunity. Now, moving in the active regime, we're not taking one sample mask for all the images, but instead we sample one line at a time in the image and then accumulate samples in that sense. After every step, reconstructing an image, and based on that, taking a new sampling action. And that's what you see in this slide, where the target is shown on the right. To the left of that, the reconstruction, then the cumulative line sampling to the left of that, and on the far left, the original K-space. And comparing this method that we use for active sampling, which was again based on this Gumbel softmax trick, so the Gumbel categorical sampling trick, we compared our method to several other active baselines, so methods that use active acquisition, and even our own, say, fixed learned sampling scheme. And this active acquisition outperforms the fixed learned sampling, which in turn actually outperforms also the other active methods. So it shows you the power not just of the model-based optimization scheme, and not just of the active sampling, but also of the sampling mechanism based on Gumbel top K. Now that brings me to the end of this presentation, this lecture on deep learning for medical image reconstruction. We saw that there are several gaps in classical optimization algorithms that we can fill with learning methods. Think of augmenting, complementing, say, the acquisition model assumptions and compensating for the fact that they may not be correct or imprecise or challenging to estimate. That's the fact that statistical image priors are not sufficiently expressive, and that we can learn those priors implicitly or explicitly from data, and overcome slow reconstruction speed of iterative methods that have high complexity by unfolding them as deep networks, and thereby accelerating them greatly. We saw a couple of examples of the union, you could say, of deep learning and model-based algorithms where we integrate models into deep neural networks, as you see basically on the right, so that's deep unfolding, versus integrating deep learning into model-based algorithms, which you see on the bottom left, where we integrated this AI agent into an adaptive beamforming algorithm for ultrasound. And on the top right, say more future perspective towards even active acquisition and systems that learn how to take measurements in a clever way to then subsequently produce value in terms of the best image quality. Thank you for your attention, and enjoy the rest of this spring school. Thank you.